Hey guys, welcome to this video. I'm calling it complex quadratics because there's really a lot of stuff that's covered in here, so we'll go as we go along. But there's completing the square, quadratics, discriminates, finding quadratic equations with certain roots, and solving for quadratics that are more complicated. So we're just going to start off by completing the square. And before we start, I'm just going to show you the format that we really want this to look like. We want this to look like x minus b squared equals c, right? So we want this so that we can square root both sides. We can get x minus b equals plus or minus root c, and then we can just get x equals plus or minus root c plus b. So obviously it's a lot simpler than like solving for a whole quadratic equation, so that's what we want it to look like in the end. So I'm going to show you how we're going to get there. So first, we really want the coefficient on the x squared to just be 1. So we're going to divide everything by 2. X squared minus 7x plus 3 halves equals 0. Okay, now we're going to try and get the 3 halves over to the other side. So we're going to do x squared minus 7x plus blank equals negative 3 halves plus blank. And we want this because we want to be able to make this side look like something squared. But we also have to add whatever we add to this side to this side. So we need those to be in both places so that we're not actually altering the equation in any way. So what we really want this to look like is x minus 7 halves. Because if we have this and we have this squared, then this becomes x squared when it's written out minus 7 halves x minus 7 halves x plus 7 halves squared. Right? And then when these combine, we just get x squared minus 7x, right? Because these two are combining, plus 7 halves squared, which is what we want because we already have these 7x up here. So now all that we need to add is the 7x squared. So I'm just going to erase all this. Okay, and we're going to keep the x minus 7 halves squared. And when we square 7 halves, I just like to keep it as like 49 fourths. I just like to keep it as 49 fourths. And this way we can just add it to the other side easily. So I just keep it as plus 49 fourths. Okay, now when we add this to the other side, I like to combine these two and making this minus 6 fourths plus 49 fourths. So we have a similar denominator, so it's really easy to combine. And then this just becomes 43 fourths. So now when we square with both sides, we get x minus 7 halves equals root 43, plus or minus root 43, never forget that, over 2. And then we add to the other side, we get x equals plus or minus root 43 over 2. And then because the 7 halves has a similar denominator, we're just going to add 7 right on here. So our two solutions are going to be x equals positive root 43 plus 7 over 2, and x equals negative root 43 plus 7 over 2. So that's it for completing the square. That might seem a little complicated, but it's really not that bad if you try it a few times. Basically, the thing that you always want to make sure is that you get this format correct, so you have this x minus whatever squared, and that you add whatever you need to add to be able to square it on both sides. Okay, next we're going to be looking at a quadratic equation. I think most of you guys have done quadratics, so I'm going to make this one quick. Basically, the formula is x equals negative b plus or minus the square root of b squared minus 4ac over 2a. And when we look at this, we can see that our b value is negative 7, so it's just going to be x equals 7 plus or minus the square root of 7 squared, which is 49, minus 4 times 5 times 9, all over 2 times 5, which is 10. Okay, now when we simplify this, we get x equals 7 plus or minus, and we actually get 49 minus 180, which is root negative 131. All over 10. Okay, but now if we have a negative inside of a root, we're going to need to pull that negative out. So we actually get x equals 7 plus or minus I root 131, right? Because we can pull the negative 1 out, all over 10. So our two solutions are going to be x equals 7 plus I root 131 over 10, and x equals 7 minus I root 131 all over 10. So that's really not that bad. I think the biggest thing on your test, there are going to be quadratics, and they're going to have imaginary numbers in them, because otherwise it's going to be really easy. So making sure that you can pull out those imaginary numbers and find the two roots with that. Okay, next we're going to look at the discriminant. So the discriminant is really just a portion of the quadratic equation which kind of tells you a lot about the roots of the equation. So if we look at the actual equation, we get x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And I'm actually going to color this discriminant in a different color because I think we really need to look into just this. Okay. So our negative b and the 2a don't really tell us anything about each individual root. They tell us about the roots together. But the plus or minus is what really tells us about each individual root, because we have one root that's a plus and one that's a minus. So we get two solutions, one with plus, one with minus. And these are basically determined by the discriminant. So if our discriminant is equal to 0, so if root b squared minus 4ac is equal to 0, right, then we really only have one real root. So we're going to look at an example of that really quick. So if we have like 5 plus or minus root 10, and this is not accurate, but just go along with me here, 10 minus 10 all over 2, right? Then this becomes 5 plus or minus root 0 over 2, which just becomes 5 over 2, because the plus or minus is gone, because if you're adding and subtracting 0, there's really no difference. So if the discriminant right here is equal to 0, we're only going to have one root. Right? Okay. Now, let's look at what happens if the discriminant is greater than 0. So, if we're saying that b squared minus 4ac is greater than 0, then this is going to have two real roots, and I'm going to show you why. So, if we look at this example, 6 plus or minus root 46 minus 10 over 2. Again, this is not a realistic example, but that's okay. Then we get 6 plus or minus root 36 over 2, which is just 6 plus or minus 6 over 2. So then our two solutions are 12 over 2 and 6 over 2. 0 over 2. So we clearly have two distinct solutions here, 6 and 0. Both real solutions, both real roots, and this is because the discriminant is greater than 0. Okay, now let's look at a case where we have a discriminant that's less than 0. And I think this one's probably the most obvious because it just kind of makes sense. So if it's less than 0, we're going to get two imaginary roots, and here's why. So let's say that we have 6 plus or minus 10 minus 46 over 2. So kind of the opposite of the last one. Then we have 6 plus or minus root negative 36 all over 2. And if we simplify this, we get that this is equal to 6 plus or minus 6i over 2. Because this negative comes out and it becomes imaginary. So whenever you have a negative inside of a root, it can't be a real solution, right? So right here, this makes the solution imaginary, and it always does. So because this is the discriminant, if our discriminant is less than 0, it's always going to be imaginary. So we're going to look at a quick example, and we're going to just find, without solving for the roots, we're going to find whether the roots are real, non-real, irrational, or rational, and the number of roots. So this is on your worksheets on the back, I think. So we have 7x squared minus 8x plus 2. So again, we don't want to solve for the roots. All that we want to do is look at the discriminant. So the discriminant is going to be b squared minus 4ac. And we're going to look if that's greater than, less than, or equal to 0. Okay, so b squared is 64. And minus 4ac is minus 4 times 7 times 2. So 64 minus 56 is also equal to 8. And if we look at 8, we know that it's positive, right? So we're going to know we have two real roots. And then if we actually think about this, so our discriminant is inside of a root, right? So if we have root 8, this is not going to be a rational number because it's going to give us an everlasting trail of things. And really, the only time that it's rational is if you have a perfect square. So if you have like root 9 or like root 16, then you're going to get whole rational numbers and they're going to be integers. So when you have something like root 8, you're not going to get a rational number. And again, there are cases where like if you had 1.5 squared, then that's 2.25, like, yeah, that's going to be a rational number. But something like root 8 is not going to be a rational number. So we know that this is an irrational number. So we know that has 2 roots and that it's irrational. Okay, let's look at our next example. This is that find k such that there are 2 imaginary roots of x squared plus kx plus 9. And we want to find k so there are 2 imaginary roots. So x squared plus kx plus 9 equals 0. Okay, so we want b squared minus 4ac to be less than 0. And this is the way that we're going to get 2 imaginary roots. So we're obviously going to have some sort of inequality here and some sort of range here because obviously there are multiple values that are going to give us imaginary roots. So we plug in some of our stuff. We get k squared because that's b right now, right? So we get k squared minus 4 times 1, because the coefficient in a is 1, and we're going to multiply that by 9. And we're saying this is less than 0. So we're saying k squared is less than, if we combine this out to the other side, k squared is less than 36. So if we root both sides, we get k is less than positive root 6, and k is greater than negative root 36, and positive root 36. So then we get k is less than 6, and k is greater than negative 6. So we get a range. K is less than 6, and it's greater than negative 6. So here we go. This is how you find k such that there are 2 imaginary roots. Okay. So the next thing that we're going to look at is finding equations when you're given roots. So you guys probably learned about this in class, but I'm just going to do a brief review. So when you have x1 times x2, right, your 2 roots, if you multiply them together, you get c over a. And this is something that I think you were probably told to memorize. They might have done a quick derivation, and if so, honestly, feel free to skip this section, or if you just don't want to look at it, feel free to skip it. But if you're having trouble memorizing this, I would consider watching the derivation because it's really very simple, and I actually figured it out just thinking about it. I was like, I think this could be derived, and it actually can. So if we're looking at the 2 terms, x1 and x2, I'm going to set x1 equal to negative b plus b squared minus 4ac all over 2a. And I'm going to set x2 to negative b minus root b squared minus 4ac all over 2a, right? So we have one of the positive and one of the negative solutions, which is what you're always going to get when you solve a quadratic, right? So we're saying if we multiply these 2 solutions, we should get c over a, because this is just the most basic level. So if we actually do that, negative b plus root b squared minus 4ac all over 2a times negative b minus root b squared minus 4ac all over 2a. This is actually a difference of squares here, right? So we see this positive and negative here, and our first and last terms are the same. So this actually becomes really nice. This just multiplies to be b squared, and then because there's a difference of squares, so we don't have to worry about the middle terms, we just get minus root b squared minus 4ac squared, which just becomes b minus b squared minus 4ac. And if we multiply the bottom terms, we get 4a squared. So now if we multiply this negative through, we get b squared minus b squared plus 4ac all over 4a squared, which equals 4ac over 4a squared. That cancels out, the a cancels out, and the squared cancels out to give us c over a. So it's kind of a nice derivation there. I thought that was pretty simple because normally I can't really understand where the derivations are coming from, but that one I could. So if we have x squared plus, okay, so we have x1 and we're adding x2. So if we look back to our previous one where we set x1 equal to negative b plus and x2 equal to negative b minus. So I'm just going to write that out here because I don't feel like writing those out again. So I'm just going to do negative b plus root b squared minus 4ac all over 2a plus negative b minus root b squared minus 4ac all over 2a. So we can't add them because they're like denominators, so that makes it kind of nice. And when we add them, we're actually going to get that our positive root and our negative root cancel out. So then we're just left with negative 2b over 2a, which just gives us negative b over a. So obviously this is a super simple derivation, and I think it's pretty helpful if you don't remember, oh, is it positive or negative? You can always just try this on the test. And now we're going to do a few examples. And really, this isn't that bad. You just have to remember negative b over a and c over a. Okay. So, with our first example, it says find a quadratic equation that has the roots of 7/5 and negative 3/4. So first we're going to find b and a. So if we have 7/5 and we are adding negative 3/4, we are going to get negative b over a, because we're adding the roots, right? So now what I like to do with this is find a common denominator. So if we make our common denominator 20, we get 28 over 20 minus 15 over 20 equals negative b over a. And then you get 13 over 20 equals negative b over a. A is going to equal 20, and b is going to equal negative 13. And a, you could say, oh, well, what if there's some weird factor on a, or like what if it's multiplied by something? We're going to check that in our next looking at the c over a just to make sure, but usually it's going to end up that a is the same in both places. So now if we have 7/5 times negative 3/4, that's going to be equal to c over a. When we multiply them, we get negative 21 over 20 equals c over a. So obviously a is going to be the same thing. A just equals 20. C is going to equal negative 21. And if we write our equation, we get 20x squared minus 13x minus 21 is equal to 0. So really not that bad. Okay, now we're going to look at solving quadratics. So first we have x to the 4th minus 81 equals 0. So if we just start to factor this, we get x squared minus 9 times x squared plus 9 equals 0. Okay, now in the future, or in the past, what we do is we just cross this out and be like, okay, can't do that. So not anymore. Now we actually have to find all the possible solutions in the real and imaginary realm. So if we set x squared minus 9 equal to 0 and x squared plus 9 equal to 0, this one's obviously easy. X minus 3 times x plus 3 equals 0. X equals 3, negative 3. Okay, now this other one is a little bit harder, but it's really not that bad either. So if we look at it, you're going to get x minus 3i times x plus 3i equals 0. And just looking at why this makes sense, if we multiply this through, we get x squared minus x, I'll do 3ix, plus 3ix, kind of did that backwards, minus 9i squared. So your middle terms cancel out. So then you're left with x squared minus 9i squared. Okay, and then when you simplify this just becomes x squared minus 9 times negative 1, because I squared is also equal to negative 1. And so then this just becomes x squared plus 9. And that's exactly what we want. So that's actually perfect. And so that's what you do when you have a plus and you want to create a difference of squares. So we just have x equals 3i, negative 3i. Those are our solutions. So we're going to have 4 solutions for that, which makes sense because it's to the 4th power. Okay, our last example, this one I personally think is actually harder than the one to the 4th. So we have x cubed minus 27 equals 0. So we can factor this to become x minus 3 times x squared plus 3x plus 9 equals 0. Okay, so in the past, again, we'd cross this solution out and be like, okay, doesn't work. Because that is in the imaginary realm. Because if we look at the discriminant, we get 9 minus 4 times 9 is 36. So that's going to equal negative 27, right? So normally we'd be like, okay, that's imaginary, that doesn't work. However, this time we can actually solve it. So we know that this is x equals 3. And then we're going to solve the quadratic equation to find the other solution. So if we have x equals negative 3 plus or minus root 9 minus 36 all over 2, that becomes x equals negative 3 plus or minus root negative 27 all over 2. And this is x equals negative 3 plus or minus 3I root 3 over 2, right? Because we're pulling out a negative 1, which gives us I, and we're pulling out a 9, which gives us 3. And these are going to be our final answers. So if we want to really write these out, we can get x equals 3, comma, negative 3 plus 3I root 3 over 2, comma, negative 3 minus 3I root 3 all over 2. So there you go. Those are our solutions. Hopefully this video is helpful to you. And there are some harder questions on the practice test, which is also posted on the website. And good luck.